Hello everyone, today we are going to look at eigenfunctions of LTI systems, definition of continuous time Fourier series or CTFS, the synthesis and analysis equations for CTFS, and the properties of continuous time Fourier series. Let's first take a look at the motivation behind developing Fourier series and how eigenfunctions of LTI systems fit in this context. So suppose that we find a rich family of signals, we call them x sub k of t, such that when you apply these type of signals to an LTI system, the output is going to be the scale version of the input. So for example, when you apply x1 of t, For example, when you apply x1 of t, the output is going to be the scale version of x1 of t. And lambda k is a scalar factor. Or if you apply x2 of t, again, the output is x2 of t multiplied by another scalar factor. And next, suppose that you can write a general arbitrary signal x of t as a linear combination of these base functions or family of the signals that you found for your LTI systems. Next, we want to know what is going to be the response of the system, this LTI system, to x of t if we have both of these conditions satisfied. That means if we find the base signals such that when you apply them to the LTI system, the output is going to be the scale version of this base function. And on top of that, you can write a general signal, an arbitrary signal, as a linear combination of these base functions. So what do you think is going to be the output of LTI systems when you apply this input signal? Okay, for every xk of t, for every component in this summation, in the summation of x of t, when it is applied to the LTI system, the output is going to be the same component multiplied by a scalar. Now that you have a linear combination of these components, the output is going to be a linear combination of similar component. Is just scaled by a factor of lambda sub k. So the output is going to be a linear combination of lambda k multiplied by xk of t, which this expression lambda k xk of t is the response of the LTI system to xk of t. Okay. Keeping that in mind, we would like to start reviewing and learning about eigenfunctions of LTI systems. By definition, in an LTI system, if the output signal is the scale version of the input signal, then the input function is called an eigenfunction of the system, and the scaling factor is called the eigenvalue of the system. Now let's investigate the output of a continuous time LTI system to the input signal that has this format. It's in the format of this complex exponential. X of t is equal to e to the st, where s is a complex number. For example, s equals to a general complex number. I'm going to show it with alpha plus j omega. As an example, you can think about it as s equals to 1 plus 2j, or any complex number. Let's find the output of the system to this input signal. Because this is an LTI system, we can write the output as the convolution of impulse response with the input signal. So y of t is h of t, which is the impulse response of the system, convolved with x of t. That's going to be equal to integral in negative infinity to plus infinity h of tau x of t minus tau d tau. And then your x of tau here is e to the st. So x of t minus tau is e to the s t minus tau. All right. Continuing with that, y of t is going to be equal to integral of h of tau e to the s tau multiplied by e to the st multiplied by e to the negative s tau d tau. Okay, so this e to the st does not depend on tau, so we can take it out of the integral. And then we're going to have y of t is equal to e to the st, which has time dependency, so it depends on t, all right, multiplied by an expression that does not depend on t. So with respect to t, it's a constant number, which happens to be a complex number in general, all right. With that, we end up with this expression for a y of t, and if we define h of s as the answer for this integral, then we can write y of t equals to h of s multiplied by e to the st. This h of s does not depend on t, and it's a complex number in general. So the output of system for x of t in the format of e to the st is e to the st multiplied by a scalar factor. This scalar factor h of s is called the transfer function of the LTI system. And h of s is determined by using the impulse response of the system. Okay, so in the top picture you can see that e to the st is applied to the system, and at the output you get h of s multiplied by e to the st. So using the definition of eigenfunction, we can show that e to the st is the eigenfunction of any continuous time LTI system, and h of s is the corresponding eigenvalue, because e to the st goes to the system, and the output is equal to e to the st, the same function, multiplied by a scalar factor. So it's e to the st is an eigenfunction of LTI systems. Okay, so if we know that s is a complex number in general, so if we focus on the purely imaginary value for s, in general, s is equal to alpha plus j omega, a complex number. But if we focus on s values that are purely imaginary, we specialize to the subclass of periodic complex exponentials that are in the format of e to the j omega t. Omega is a real number in here. For these eigenfunctions, the corresponding eigenvalue, or h of s, for s equal to j omega, is equal to h of j omega, and that's equal to this integral. We have the integral that we used to find the value of h of s, that define h of s. Okay, in that integral, we're going to replace s with j of omega. Now, h of j omega has a special name. H of j omega is called the frequency response of an LTI system. In the future lectures, you're going to see the more general formats for h of s, in which s is a complex number, and it's not purely imaginary. All right, so now that we had all of these, we found these eigenfunctions for continuous time LTI systems, let's investigate the output of a discrete time LTI system for a special type of signal. The signal that we're looking at is z to the power of n. So we would like to see what happens to the input signal in the format of z to the power of n when you apply it to a discrete time LTI system with impulse response of h of n. In other words, we want to find the output y of n for this input signal. Because this is an LTI system, we know that the output is equal to the convolution of x of n and h of n. All right? And y of n is equal to sigma h of k and x of n minus k, multiplied by x of n minus k. X of n is z to the power of n, so you're going to calculate y of n by multiplying h of k to z to the n minus k and summing it for all values of k. So moving on, I see that z to the power of n is multiplied by the other factors that have k dependency, and z to the power of n does not depend on k, and this summation is over k, is running for different k values. So I can take it out of the summation. And if you do that, you're going to have y of n equals to z to the power of n multiplied by some expression that doesn't depend on n. So I wrote it in here again. So now, if I define h of z as the answer of this summation, h of e is sum of h of k, z to the power of negative k. H of k in here is the impulse response of my LTI system. Then y of n is going to be equal to h of z multiplied by z to the power of n. And this z to the power of n is in fact the input signal that I initially applied to the system, and I wanted to find the output of this LTI system for that input signal. It's here. All right. So h of z is called the transfer function of discrete time LTI systems and is determined by the impulse response, or h of n, and it is independent of the value of n. So you see, you apply z to the power of n to LTI system. At the output, you receive z to the power of n multiplied by a scalar factor, which doesn't depend on the value of n. It's a complex number in general. Okay. Using the definition of eigenfunction, we have shown that z to the power of n is an eigenfunction of any discrete time LTI system, and h of z is the corresponding eigenvalue. Now we're setting z equal to e to the j omega, so it's a complex number with amplitude of 1. Now, if we do that, we specialize to a subclass of periodic complex exponentials in the format of x of n equals to e to the j omega n, in which omega is a real number. For these eigenfunctions, the corresponding eigenvalue, or h of z equal to e to the j omega, h of e to the j omega is going to be equal to h of k multiplied by e to the j omega k, running for all, I'm summing it for all k values. So h of e to the j omega is called frequency response of LTI system. So this is the subset of h of z values in which z is equal to e to the j omega. All right, so let's move on to the continuous time Fourier series and see how we can find the Fourier series of continuous time signals. Okay, so if you remember, we wanted to find a set of base functions such that when we apply them to the LTI systems, the output is the scaled version of those base functions. And then we also were interested in writing any arbitrary signal as a linear combination of those base functions. We saw that complex exponentials can be those base functions. They are eigenfunctions of LTI systems. Now the question is, how can we decompose signals into some of those exponentials, or eigenfunctions of LTI systems? Okay, so which signals, continuous time signals, can be expressed as a linear combination of complex exponentials? The question is, for what signals we can write this expression? So the periodic signals with period of t equal to 2 pi over omega naught, this is this omega naught, that have finite energy over one period, or the signals that satisfy the Dirichlet conditions, we can write x of t as summation of scalar factor ak multiplied by e to the jk omega naught t, a large class of signals, and the ones that we are going to use in this course can be written in this format, and we can write this expression for those signals. Please read section 3.4 of your textbook to get more information about which signals can be represented as a linear combination of complex exponentials. Okay. So for any periodic signal x of t with period of t greater than 0 that has a finite energy over one period, you can write x of t as summation of ak e to the jk omega naught t, where AK can be calculated as 1 over t integral over 1 period t x of t e to the minus jk omega naught t d of t. In this expression, omega naught is 2 pi over t, and t is the period of your input signal. Remember, this is a periodic signal with period of t, and omega naught in here is 2 pi over that period. So equation 1 is called the Fourier series representation of x of t, and coefficients, AK coefficients, are called the case Fourier coefficient of x of t. AK values are unique. All right. In summary, for a periodic signal x of t with fundamental period t and fundamental frequency of omega naught 2 pi over t, synthesis equation is x of t equal to sigma ak to the jk omega naught t. The analysis equation is ak is equal to 1 over t integral over 1 period x of t e to the minus jk omega naught t d of t, and we show them the notation that we use is in this format. Fourier series of x of t are going to be represented with AK. It's not unique. AK values are unique, but the letter or the notation that we use to show the Fourier series coefficients are not unique. So you can show the Fourier series coefficients of x of t with BK, CK, or anything that you like. Generally speaking, AK is used to show the Fourier series coefficients of x of t. Let's take a look at an example of finding the Fourier coefficients of a periodic continuous time signal. So the question asks us to find the Fourier coefficients of this periodic signal. X of t is 1 plus 1 over 3 cosine of 2 pi t plus sine of 3 pi t. So if your signal, continuous time signal or discrete time, doesn't matter. So if your signal is provided in the sine and cosine format, in a sinusoidal format, it's easier to find the Fourier series coefficients if you write x of t in the format of complex exponentials, then compare the components, each component in x of t with the components of the synthesis equation. I'm going to do it now, and you will see how you can compare it and extract the values of AK. If x of t is not in the sinusoidal format, then you need to write the analysis equation to find the AK values. All right, so first I need to find the period of this signal. Pause the video and find the period of this signal. All right, so x1, I'm going to name cosine of 2 pi t as x1 of t, and I want to find the period of this one, and then I'm going to name sine of 3 pi t as x2 of t, and I'm going to find the period of this one separately, and then the period of the entire signal x of t is going to be equal to the least common multiple of the period of the fundamental period of each one of them. All right, so I'm going to name the fundamental period of this one as t naught 1. That's going to be equal to 2 pi over omega naught 1. That's going to be equal to 2 pi over 2 pi. That's going to be equal to 1. The fundamental period of the second signal is equal to 2 pi over omega naught 2. That's equal to 2 pi over 3 pi, and that's 2 over 3. Okay, so least common multiple of 1 and 2 over 3 is equal to 2. So the fundamental period of this x of t is equal to 2, and the fundamental frequency is equal to 2 pi over 2, which is equal to pi. All right. Now I'm going to write x of t in terms of complex exponentials. To do that, you can use Euler formula. So here I provided the way that I'm going to use the Euler formula to write this sine and cosine functions in the form of complex exponentials for your review. But I have x of t equals to 1 multiplied by e to the j to the power of e to the j multiplied by 0, because 1 is multiplied by 1, plus 1 over 3 multiplied by, instead of cosine of 2 pi t, I'm going to write e to the j 2 pi t plus e to the minus j 2 pi t divided by 2 plus, instead of sine of 3t, I'm going to write e to the j 3 pi t minus e to the minus j 3 pi t divided by 2j. All right, so I wrote x of t in terms of complex exponentials. Next step is to write the synthesis equation and compare these components with the components of synthesis equation and extract ak values. Let's do that. Here is my synthesis equation. X of t is equal to sigma ak e to the j k omega naught t, and it's running for k equals to negative infinity to plus infinity. I know the value of omega naught. I just calculated it. It's equal to pi. So this summation is equal to ak multiplied by e to the j k pi t for k equals to negative infinity to plus infinity. All right, let me write some of these components for you to see. That's equal to a lot of components here plus, I'm starting from a negative 4. For k equal to 4, I'm going to have a negative 4 e to the minus j 4 pi t. For k equal to negative 3, I have a negative 3 e to the minus j 3 pi t. For k equal to negative 2, I have e to the j minus j 2 pi t plus a negative 1 e to the minus j pi t plus a sub 0 e to the j multiplied by 0 multiplied by pi by t, so it's j multiplied by 0, plus a1 e to the j pi t plus a2 e to the j 2 pi t plus a3 e to the j 3 pi t plus all other components. So this expression is the general expression for the synthesis equation of for any x of t, but the x of t that I'm given here is 1 plus 1 over 3 cosine of 2 pi t plus sine of 3 pi t. So in my x of t, I have 1 multiplied by e to the j multiplied by 0 plus 1 over 3 multiplied by 1 over 2 e to the j 2 pi multiplied by t plus 1 over 3 multiplied by 1 over 2 multiplied by e to the negative j 2 pi t plus 1 over 2j e to the j 3 pi t plus, and then there is a negative here, minus 1 over 2j e to the minus j 3 pi t. Let me draw a line in here so we can separate it. All right. And then our job is to compare these two and then extract the coefficients. Oh, okay. All right. Okay, so I see this exponential in the given x of t, and I have it in here for the generic synthesis equation that I have for any x of t. So whatever I see in here for the coefficient of e to the j0 is going to be my a sub 0. With that, I have the value of a sub 0, which is equal to 1. Moving on, I see this coefficient in here, which which matches this coefficient in my generic synthesis equation. So the coefficient of this term, or this complex exponential, is my a2. So this is my a2, and this is my a sub 0, right? Continuing in the same manner, for e to the negative j2 pi t, I have it in here. So this coefficient is in fact a negative 2. Continuing the same way, e to the j 3 pi t is here. So that coefficient, this coefficient is a sub 3. And then this one, e to the negative j 3 pi times t is this, the same one than in here, and then this coefficient is my a negative 3. So I found all of the Fourier series coefficients by comparing them with the synthesis, the components of the synthesis equation. With that, I can write all of the Fourier series coefficients for the given x of t. A sub 0 is equal to 1, a2 equals to 1 over 6, a negative 2 equals to 1 over 6, a3 equals to 1 over 2j, and a negative 3 equals to negative 1 over 2j. Here's another example for a periodic continuous time signal, which is not in the format of a sinusoidal signal, and we would like to find the Fourier series coefficients of this signal. And because it's not in the sinusoidal format, we have to use the analysis equation, which is ak equals to 1 over t integral over one period x of t e to the minus j k omega naught t, and omega naught is the fundamental frequency of x of t, the periodic signal. And all right, so I'm ready to evaluate this integral. I need to find the fundamental frequency of the signal or fundamental period of this signal, the given x of t. And if you look at x of t, the fundamental period here, t naught is equal to t, and omega naught is equal to 2 pi over t. All right, so it repeats every uppercase t points. All right, so I'm going to write ak is equal to 1 over t integral. I only need to evaluate this integral in one period, so I'm going to choose this period that's convenient to find the answer of this integral. So I'm going to focus to evaluate my integral from negative t over 2 to t over 2. And then it's going to be x of t integral multiplied by e to the minus j k 2 pi over t multiplied by t d of t. Okay, so x of t is only non-zero between negative t1 and t1 in here, and the amplitude of x of t or value of x of t in that period is equal to 1. So it's going to be 1 over t integral between negative t1 and t1. The amplitude of x of t is equal, or the value of x of t is equal to 1. It's a real signal. 1 multiplied by e to the minus j k 2 pi over t multiplied by t dt. All right, let's evaluate this integral. So I rewrote the same equation in here. That's going to be equal to negative 1 over t multiplied by j k omega naught. And then I am calculating the value of negative j k omega naught t from negative t1 to t1. That's going to be equal to negative 1 over t j k omega naught multiplied by e to the minus j k omega naught t1, and that's t1, minus e to the j k omega naught t1. All right, that's equal to minus 1 over t j k omega naught multiplied by, I'm using Euler's formula here. The value of the expression inside this summation, inside the parentheses, is equal to negative 2j sine of k multiplied by omega naught multiplied by t1. So AK coefficients are equal to 2 sine of k times omega naught multiplied by t1 divided by k times omega naught multiplied by t. AK coefficients are real for this signal, but generally speaking, Fourier series coefficients are complex in general. For this specific signal, AK values are real. All right, so the only problem is finding the value of a sub 0 here, because if you substitute k with 0 in this expression, both the numerator and denominator are going to be equal to 0. But we can use the analysis equation for k equal to 0 and calculate a sub 0. Using the analysis equation, I have a sub 0 equals to 1 over t, integral of negative t1 to t1, x of t multiplied by e to the minus j. I had j k omega naught t. Instead of k, I'm going to write 0 multiplied by omega naught, which was 2 pi over t multiplied by t dt, which is 1 over t integral of negative t1 to t1, 1 multiplied by 1 multiplied by dt. That's going to be equal to 2 times t1 divided by t. So that's the answer for a sub 0. You could have also used the L'Hopital's rule for calculating a sub 0 from the expression of AK. I'm going to provide it in here, and then please practice it. All right. So next we are going to look at the properties of Fourier series. Please read section 3.5 of your textbook and to see the proofs. The linearity property of Fourier series says that if the Fourier series coefficient of x of t is denoted by AK and Fourier series coefficient of y of t is denoted by b sub k, then Fourier coefficients of alpha x of t plus beta y of t are going to be equal to alpha ak plus beta bk. And time shifting property says if Fourier coefficient of x of t is denoted by ak, Fourier coefficients of x of t minus t naught is going to be equal to ak multiplied by this complex exponential. Time reversal says if Fourier coefficient of x of t is ak, then Fourier coefficient of x of negative t is a sub negative k. That means if you have an expression for ak, the equation of ak, you're going to substitute k with negative k in that expression. Or if you have the graph of ak, it's going to be the flipped version of the same graph. Time scaling says if you scale x of t in time by a factor of alpha, which is a positive number, I put an exclamation mark in here just to note that this alpha in here is positive and the period of x alpha t is t over alpha. All right, so the Fourier coefficients of the signal is not going to change. And then multiplication property says if we denote Fourier coefficients of x of t with ak, then Fourier coefficients and Fourier coefficients of y of t with bk, then the Fourier coefficients of x multiplied by y is going to be equal to convolution of ak with bk. The conjugation says the Fourier coefficients of x conjugate of t is going to be equal to a conjugate of negative k. All of these properties are provided in table 3.1 of your textbook. Please review them. Right. One of the most important properties is Parseval's relation, which says for a periodic signal x of t, which can be written as using the synthesis equation as sigma ak e to the j k omega naught t, for k between negative infinity and infinity, we have 1 over t integral over t of a magnitude of x of t to the power of 2 dt. It's going to be equal to summation of ak, magnitude of ak to the power of 2. In this expression, magnitude of ak to the power of 2 is equal to 1 over t integral over t of magnitude of ak e to the jk omega naught to the power of 2. Parse-Weill relationship says that energy of a signal is equal to the sum of the energy of its harmonic components. All right. So in the class, we are going to practice using these properties in solving problems. Thank you for watching.